So we're going to pick back up problem 10.19. We're going to look at designing the motor circuit. So we're going to design our motor circuit. And we're going to design this per the NEC 430 requirements. Okay, so there's specific components we need and specific power and current ratings we need for those components per the NEC 430. Okay, so we're going to follow those. So the really five elements that we're going to want to consider in our circuit. We talked about these in the lecture presentation. Kind of line these up here. We have our disconnect. We have our short circuit protection. We have our contactor, which is our switch to turn the motor on and off. We have our overloads. The fifth element, of course, are the conductors that connect all of these things together. These are the five things you're going to want to consider when you're working through the homework for this week. So we're going to go through each of these. We want to have a distinct label for each of them. So we'll do a disconnect, two-pole, right, because we have a 240 single phase, black and a red. We have a circuit breaker for our motor short circuit protection. We're going to have a contactor, CON, for our switch. We have overloads. Okay, so each of these is drawn as two poles. When we actually look at part numbers, we may have to get a 3-pole or a 4-pole for some of these and just wire up only 2 of them. And in your circuit, you only show the number of poles you need to wire. So looking at the disconnect to start, if we go back to our slide presentation, we need our disconnect, the current rating of our disconnect, to be greater than or equal to the full load current times 115%. Now this full load current must be from our NEC table 430 248, because we're using our single phase, right? Our circuit's a single phase circuit, so we want to use our single phase table. You're going to use a 3-phase table when you do your homework. But looking at the 7.5 horsepower motor, we would come across, so 7.5 horsepower motor, come across to 40 amps, because that's our 230, 240, right? We can estimate that to the 40 amps. Okay, so we're going to use 40 amps for our full load current. So 40 amps, 1.5 equals 46 amps. So we need to have a disconnect that's rated at least 46 amps. We also need the horsepower of our disconnect to be greater than or equal to the horsepower of our motor times the service factor. And so we have a service factor or a horsepower rating of 7.5 horsepower, service factor of 1.15. If we look back at our motor we selected, we have a service factor of 1.15. So we'll do that calculation, and that comes out to roughly 8.625 horsepower. So we want a horsepower that's at least rated for that. So we'll usually go up. Most likely we'll find a 2-pole disconnect rated at 63 amps and a 10 horsepower. Okay, most likely you're going to find something in that neighborhood. Really, you just want to get the amperage and the horsepower rating above what these numbers are calculated at. So now turning to the short circuit protection, our circuit breaker. Okay, so we have our disconnect, we have our circuit breaker, and these correspond to the tags I'm giving up in this drawing. Okay, just to note, these dashed lines mean they're mechanically connected. Okay, so they're part of the same component. So short circuit current rating, we need our short circuit current rating for our circuit breaker, if we're using a circuit breaker, to be greater than or equal to a full load current times 115%. This is the minimum, so this is a minimum. There's a maximum of 250, but usually what I like to do is to start at my minimum and just get the next value up in the catalog. I just can't go past 250%. So my 46 amps I need to be accounting for. And I will probably find 2-pole circuit breaker in the 50 amp range. Okay, I won't get 46, I won't get 47, I won't get 40, I'll get 50 amp circuit breaker. So there's our circuit breaker, our short circuit protection. And now we're going to turn to our contactor. It's the third element in the circuit. That's our CON. And for contactors, we need to account for a current rating greater than or equal to, again, the full load current times 115%. Okay, so that what we found, that's going to be our 46 amps. Our horsepower rating, again, needs to be greater than or equal to our motor horsepower times our service factor. Okay, we looked at this previously as our 8.625 horsepower. So most likely, and when you get contactors, they'll come in a 4-pole flavor, so they can be used for 3-phase if you need to. Plus the fourth one is just an auxiliary. Most likely you'll have a 63 amp. That's a common amperage value when you get up into the 40, 50 amp ratings. And then a coil voltage. Contactors have a coil that you use to energize. You put power to the coil and they close. So the contactor is open, you energize it, it closes, and current goes through it. So if we look at our circuit, they're shown open, right? Once you energize the coil, those contacts close, and that makes connection between those 2 points. And we looked at those in class, okay? We talked about overloads. We'll talk more about those after exam 2, though. Basically, for our system, 240 volt coil, because we're going to wire it up to the 240 power lines for the motor. Okay, there's our contactor. We go find a part, 4-pole, 63 amp, 240 volt coil. Overload relays. So what we need, those are the OLs, overloads. We need a current rating greater than less than or equal to current full load times 125%. Okay, now this full load current is going to be based on the nameplate, okay, current rating of our motor. I don't have a nameplate current rating in the document online that we show here. It doesn't show us the nameplate current rating. So in that scenario, I don't know what the full load current rating of the nameplate of the motor is. I'm going to guesstimate, I'm going to estimate, I'm going to use the full load current from my NEC table. Okay, when in doubt, 40 amps. Okay, I'm going to base it off the 40 amps. So my 40 amps times 1.25, I have a 50 amp I need to consider. So for the overload relays, now because I can't go greater than, it's equal to or less than this, because I want those to trip if I get up to 50 amps, right? I don't want those to wait until it gets to 60 or 70 or 80, right? I want to trip them sooner than that because there's going to be heat buildup. I'm going to look at 3-pole, and heaters come in 3-pole flavors. Usually there's a range, and I've found a 44 to 54 amp range heaters, and so a lot of those common ones that you can buy today, you can dial in a range, right? And depending on if it's hot or cold, you can dial down or up, but that 50 amps will sit right inside our range. So our last component, right? We've talked about all the components so far in our system: our disconnect, circuit breaker, contactor, overload, but now we're going to talk about the actual conductors, right? the actual wires. If we look at the wires, or the conductors, okay, we need, going back to the original application, copper in conduit. So that's going to be our THHN, right? THHN is the kind of conductor you want to put inside conduit. So we're going to go with a THHN. The next question is, what gauge? What's going to be our gauge? So we can look at two different things, ampacity and voltage drop. One thing I failed to mention previously, we have a 120 foot dimension between our motor and our electrical panel. Okay, so 120 is our single one-way distance. Adding 10% for connection, so we have 120 feet times our 10%, 132 feet one way. Now, that's the dimension I want to use when I look at voltage drop, 2% voltage drop on the Chapter 5 tables. If I want to purchase this wire, I need to account for 132 to the motor and another 132 back to the power panel. So I need 2 times that. Okay? So times 2 equals our 264 feet, and that's our total. Total to purchase. Okay? Now, looking at ampacity. So we have an ampacity consideration. We have our full load current times the 125, okay? So we need, same as above, full load current times 125 per the NEC. Give us our 50 amps, okay? So we're going to use that 50 amp row. We're going to figure out from an ampacity standpoint, at 50 amps, we're going to want to look at our table 5.6. Nope, 5.7. We're going to look at 50 amps, and we're going to be in the THHN, 50 amps, and that's going to be 8 gauge. Okay. While we have this open, we're going to come across, and 132 feet was our one-way length, so we got to go up to 150. So we're going to come across, that's going to be our 4 gauge based on a 2% voltage drop. So 8 gauge based on ampacity, 4 gauge based on amp voltage drop. So we're going to use the 4 gauge. Okay. So we're going to end up using 4 gauge copper. And we're going to need to buy 264 feet of it. Okay. We have to make sure that we have the 125% of the full load current to get our current ampacity, and then most likely it's going to be based off of, the length when it's over 100 feet. So, just refreshing what we've done here. We've calculated and determined our disconnect, our circuit breaker, our contact, our overload, and our conductors. Now, when you go look at parts, a lot of times these two things you can get as one piece, and these two things you can get as one piece, as far as one part number. So you can get a single part number for these, a single part number for these. As long as you have a disconnect and a circuit breaker and a contact or an overload and conductors, that's what you want. Good luck with homework for this week.